Okay, number 1. It is given all of that. Show the result is true for n equals 1. So remember, this is the general term. So 1 cubed is 1 for the left-hand side. And so that's left-hand side. Right-hand side is 1 squared. 1 plus 1 squared over 4. So that's 1 times 2 squared, which is 4, over 4, which is 1. 2, same thing. We've got, so for a double I, we've got 1 cubed plus 2 cubed, which is 1 and 8, 9. So that's the left-hand side. Right-hand side is going to be 2 squared, 2 plus 1 squared over 4. So we're going to have 4 times 3 squared, which is 9, over 4 cancels 9. So left-hand side equals right-hand side, and triple I, we've got 1 cubed plus 2 cubed plus 3 cubed. So that's 27 and 8, 35, 36. So that's left-hand. And then right-hand side, we have 3 squared, 3 plus 1 squared over 4, which is 9 times 4 squared, 16 over 4. That cancels, and that's 36. So left-hand side equals right-hand side. For B, if we want to find 1 cubed up to 20 cubed, we just need to substitute 20 in as n. So we're going to have 20 squared, 20 plus 1 squared over 4. So this is with calculator. So you can do that. I think it's 441. So 100. So 44100. All right, and last one, C, find the least value of n such that, okay, so we need to put into our calculator this side, and we can maybe do it with nsolve, and we need to put in, 1 million. So when you substitute that in nsolve, you get that n is 44.2. So if you want the term that is greater than that, it needs to be the next term, 45. Okay. So for 2, it's a walkthrough. Show by mathematical induction was the thing we just did. So we show it's true for 1. So this is exactly what we did. 1 times 4 over 4, 1. We assume the result is true for n equals k. So we say 1 cubed plus 2 cubed plus ... plus k cubed is equal to k squared, k plus 1 squared over 4. Okay, and we show the result is true for n equals k plus 1. So 1 cubed plus 2 cubed plus ... plus k cubed plus k plus 1 cubed equals to k plus 1 cubed. K plus 1 is k plus 2 squared. Oops, this should be squared right here. Over 4. So that's what we want to show. So this bit here is this bit here. So I'm going to rewrite k squared, k plus 1 squared over 4 plus k plus 1 cubed. Okay, so then we will get the same denominator. So 4 over 4. And then we can take out a k plus 1 squared. Okay, so that's in common here and here. So we will have, we need a k squared for the first term. and we need, well, we can put out a 4 here. And for the second term, we need the 4, and we need k plus 1. Okay, so on this one, so we're going to have k plus 1 squared over 4. And then if we distribute this, we're going to have 4k plus 4. 4k plus 4. And we can factor that. So that's going to be k plus 1 squared on the outside. And this factors to k plus 2 squared. And that's over 4. And this is exactly what we wanted to show. So true for n equals 1. Oh, sorry, n equals k plus 1. So then we have the conclusion, and that is just going to be copied and pasted the whole way down. Okay, so for number 3, prove that 10 to the n minus 1 is a multiple of 9. So this is our proposal, and we need to show it's true for 1. So 10 to the 1 minus 1 is 9, which is a multiple of 9. True for n equals 1. For step 2, we need to assume true for n equals k. So 10 to the k minus 1 is a multiple of 9. And k is an integer. Sorry, the pen is messed up. And then for 3, we need to show all of this. So we need to show that n, it's true for n equals k plus 1. So 10 to the k plus 1, we're trying to show this is like some multiple of 9. So we can separate 10 to the k and 10, and we can fill this in for 10 to the k. So this is going to be 9b plus 1 times 10 minus 1. And when we distribute, we're going to have 90b plus 10 minus 1. And then obviously that's 90b plus 9. And we can factor out a 9, 10b plus 1. So this is a multiple of 9. So true for n equals k plus 1. So then I put that thing down there. The result is true for n equals 1, assuming it's true for n equals k. We proved it is also true for n equals k plus 1. There, I didn't even notice that. Hence, by mathematical induction, the result is true for any n in Z. Okay, so now for 4. Okay, we need to show that n cubed plus 2n is a multiple of 3. So for n equals 1, we've got 1 cubed plus 2 times 1, which is 1 plus 2, 3. So it's a multiple of 3. It's true for n equals 1. And assume true for n equals k. So we've got k cubed plus 2k is some multiple of 3. And we need to prove it's true for k plus 1. So k plus 1 cubed plus 2k plus 1. We need to make this be some multiple of 3. Okay, so if we expand this out, and if we do it by binomial theorem, all right, we're going to have, it's 1, just to review, 3, 1, that's coefficients. And then your first term's going to go down, so k cubed squared, k1, and then k0. And then our second term is going to go up, so it's going to be 1 to the 0, 1, 1, 1, 2, 1, 3, and then pluses in between. And then we're going to have plus, I'm really sorry about this one. That's a 3. 2k plus 1. Okay, so this is k cubed. This is 3k squared. This is 3k. This is just 1. And then we have 2k plus 1. So now we have k cubed plus 3k squared. Getting the k's together, that's 5k plus 2. Okay, so now we have k cubed is 3b from this step, 3b minus 2k. So 3b minus 2k plus 3k squared plus 5k plus 2. So all these are equal. So now we're going to have 3b. And negative 2k plus 5k is going to be 3k. And we have 3k squared, and we have 2. Okay, so the 2's obviously not, I did not distribute. This needs to be a 2 the whole way down. So then this 2 and this one is going to be 3 here. That's 3 and that's 3. Okay, so at least we know what we're looking for. And here we can factor out a 3 so that we have that this is a multiple of 3. Okay, so then we can say our final step. Don't forget step number 4. So and they messed up. Okay, so the next one, 5 to the n plus 3 is divisible by 4. So n is 1. We've got 5 to the 1 plus 3 is 8, which is 4 times 2. So that's true for n equals 1. And then assume it's true for k, n equals k. And we need to prove it's true for k plus 1. Oop, not 4b. Separate. 5 to the k is 4b minus 3 times 5 plus 3. Distribute 20b minus 15 plus 3, which is going to be minus 12. We can factor out a 4. 5b minus 3 divisible by 4. So we've proved it's true for n equals k plus 1. And then don't forget your fourth step. All right, so this one, we have to show 2 to the 2n minus 3n minus 1 is divisible by 9. So we have to show true for n equals 1. So 2 to the 2 times 1 minus 3 times 1 minus 1 is going to be 4 minus 3, which is 1 minus 1, which is 0, which you can write as 9 times 0. So that is true for n equals 1. And then for step 2, we can say assume it's true for n equals k. And then for 3, we need to show it's true for n equals k plus 1. So this is some multiple of 9. Okay, so if we go ahead and distribute that, minus 3k minus 3. Okay, so minus 4 here, minus 3k. And then we have 2 to the 2k times 2 to the 2. And 2 to the 2k, we can solve that. So that's going to be 9b plus 3k plus 1 times 4, minus 3k minus 4. So distributing, we've got 36b plus 12k plus 4 minus 3k minus 4. 4's go away. We've got 36b plus 9k. And we can rewrite that as 9 times 4b plus k. So that is a multiple of 9. So we've showed it's true for n equals k plus 1. And don't forget step 4. Number 7. So step 1, show it's true. So for n equals 1, so 5 plus 9 plus 2 is 14, 16, which is 4 times 4. So that's divisible by 4. Step 2, we have to assume this is true. So for A, we'll say, proposal up top. And we have to show it's true for this. Okay, so we can separate 5 to the k and 5, 9 to the k and 9, and 2. So what we want to do, we have to look back at our second step. So we need a 5 to the k and 9 to the k. And we also need these to be divisible by 4, okay? Or like the whole thing to be divisible by 4. So 5 here, there's only one multiple of 4, which is 4, and 1 will give us that 5 to the k. Here, we have two multiples of 4 within 9. We have 4 plus 5 is 9, and we have 8, which is multiple of 4, and 1. And we need that one because we have the 9 to the k up here, all right? And then we have still plus 2. So when we would distribute this, we have 4 times 5 to the k plus 5 to the k plus 8 times 9 to the k plus 9 to the k plus 2. And you see we have our 5 to the k, we have our 9 to the k, and we have our plus 2. So this in green is 4a. And we have the rest of this stuff. And we can factor out a 4. So we're going to have a plus 5 to the k plus 2 times 9 to the k, which is a multiple of 4. So we have showed it's true for n equals k plus 1. Don't forget step 4. Okay, so show it's true for n equals 1. So we have 12 plus 2 times 5 to the 0 is 1. So that's 14, which is a multiple of 7. So that's true for n equals 1. Assume true for n equals k. And, oh yeah, it's a proposal. So, or sorry, for the proposal, you could write that up at the top. And for 3, we need to show it's true for k plus 1. So we're going to have 2, 5 to the k plus 1 minus 1. So I've tried this several other ways, like the one before and the one before that, and it's not working. So what we can do, so not equal to 7a, we need to show it's a multiple of 7. So if we separate 12 to the k and 12, and we have 2, and, you know, this is like 5, so I'll just rewrite it. This is like 5 to the 1 times 5 to the k minus 1, right? So, because you add the exponents. Okay, so we're going to have 12 to the k times 12 plus 10 times 5 to the k minus 1. And the reason is because of this up there. Sometimes you just get desperate. So, if we put this in for 12k, we're going to have 7a minus 2 times 5 to the k minus 1. times 12 plus 10 times 5 to the k minus 1. So if we distribute the 12, we're going to have 84a minus 24, 5 to the k minus 1, plus 10 times 5 to the k minus 1. And we can add these two together. So we have 84a and negative 14 times 5 to the k minus 1, which you can rewrite as 12a minus 2 times 5 to the k minus 1, which is a multiple of 7. Don't forget step 4. Okay? Okay, so this one. Okay, so we need to show true for 1. So for this one, we're just doing r is 1, 2, 1, and we just substitute in 1, and that's 1. So for the right-hand side, we actually did this one in class, didn't we? So we have 1, 1 plus 1, 2 times 1 plus 1 over 6, which is 1 times 2 times 3, which is 6 over 6, which is 1. So true for n equals 1. Step 1. Step 2 is assume true for n equals k. So we've got r is 1 to k, r squared, and that should be equal to k, or we assume it's equal to this. Okay, now we need to show it's true for n equals k plus 1. So we have r equals 1 to k plus 1 of r squared. So remember, we can separate this. We go from r equals 1 to k of r squared, and we have taken away that k plus 1 term. Okay, so we're going to have to add on to that when we substitute k plus 1 into r. All right, and then this is equal to this thing. So we've k plus 1, 2k plus 1 over 6 plus k plus 1 squared. And we need to make the same denominator, 6 and 6. So now all over 6, and we're going to have k, actually we're just going to factor out a k plus 1. So on the inside, we're going to have k times 2k plus 1 plus 6 times k plus 1. And then we're going to have k plus 1. And when we distribute the k in the first bracket, we're going to have 2k squared plus k plus 6k plus 6 over 6. Oops. And then this is k plus 1. This is going to be, so here's going to be 7k in the middle. All right, so that's 7k. So what multiplies to 2k squared is 2k and k. And then we need factors of 6 that multiply, when we do the outside plus the inside, we need to get to 7. So we can have 3 and 2 here, because that's going to be outside 4, inside 3. So we need plus and plus, and then that's all over 6. So that is, well, we never wrote it down, but that is what we're looking for, because remember, I should have written it. So r equals 1 to k plus 1, r squared is going to be equal, I'm just substituting k plus 1 in here, so it's going to be k plus 1, k plus 1 plus 1, which is k plus 2, and then 2k plus 1 plus 1 over 6, and this is the 2k plus 2 plus 1, 2k plus 3. So that is this, so we showed it's true for n equals k plus 1, and don't forget step 4. All right. Number 10, use induction to prove for n greater than or equal to 2, so that's our starting point. So this is our general term. So we have to show it's true for n equals 2. So we're going to have 2 minus 1 over 2 factorial, which is 1/2. That's the left-hand side. Right-hand side is going to be 2 factorial minus 1 over 2 factorial, which is 2 minus 1, 1 over 2 factorial, 2. So left-hand side equals right-hand side. Number 2, we have to assume true for n equals k. And this should be k factorial minus 1 over k factorial. And for 3, we need to show that it's true. Yeah, this is k greater than or equal to 2. K is an integer. Now we need to show it's true for n equals k plus 1. So k minus 1 over k factorial plus k plus 1 minus 1, so just k, over k plus 1 factorial is going to be equal to k plus 1 factorial minus 1 over k plus 1 factorial. Okay, so this whole thing is going to be k factorial minus 1 over k factorial, and then we still have plus k over k plus 1 factorial. And then we need to write this as with the same denominator. So if we have k factorial minus 1, k factorial plus k over, if we write k plus 1 times k factorial, we just need to multiply this over here by k plus 1, top and bottom. So then we're going to have k plus 1 not k plus 1, so this minus k plus 1, the whole thing, plus k over k plus 1 times k factorial. Okay, so we have that this actually is k plus 1 factorial. We have minus k plus k, and we have minus 1 on top. And then again, this is k plus 1 factorial. So we've showed that this, it's true for n equals k plus 1. And don't forget step 4.